All right, ladies and gentlemen, welcome, welcome, welcome. I hope this is working. I look like I'm on about maybe about a 40-second delay from what I'm seeing here to what you should be seeing there. So fingers crossed, in about 3 seconds I'm going to see my face and we'll be ready to go. So yeah, let's go. Tonight it is Return of Physics Rocks, it's true. And the reason we're back is in 4 weeks' time we have the GCSE Double Award Unit 1 module on forces and motion and all that fun stuff with nuclear. Tonight, though, we are going to sort the first two sections of that topic area, which is motion time graphs and equations to do with that, and general forces, Newton's laws exception. All right, so thanks for the commentary, Reese, on my setup. That's the kids' computers in the background. Right, so let's get to work, shall we? Let's go. So let's get to it. So what we need to do is we need to get our way through kind of some of the general basics here. So first things first, equations you absolutely need to be able to use, know, and understand. Okay, and they start pretty straightforwardly. We have that average speed is equal to distance over time. All right, that should be a pretty straightforward one for us from pretty early down the school. You generally get that one. Okay, so technically it is total distance divided by total time, but speed equals distance over time, perfectly reasonable to use in an exam. Okay, now the most forgotten question is equation number 2 that we're going to take a look at here, which is if you have the average of any two numbers, we can do the average speed, but it doesn't necessarily need to be just the average speed, it could be anything. The average position between two numbers would be your initial speed plus your final speed, and then you would want to divide that by 2. Right. Now this is an exam trick. Okay, this question is used all the time because everybody knows average speed is distance over time. You probably get taught that in first year when you come in the door, but average speed is initial speed plus final speed over 2 is a bit more of a niche case. It doesn't get used anywhere near as much, and as a result, it's a wonderful question for exam questions to just test. Do you know everything there is to go? And it's pretty it's not a particularly difficult concept. It is the idea that if I have two numbers, right? If I have two people in my class, one of them gets 60% in the test, not in my class they don't, and the other one gets 90% in the test, and I've only got two kids in my class because I must teach at some super posh private school, then to calculate the average of those two things, I would do 60 plus 90, which would give me a total of 150. And then I would divide that by 2 to give me an average mark of 75%. And that's sort of the same here, that we have two speeds. We have a start speed, a low speed, probably if it's accelerating, it'll be a low speed, and then a larger speed at the end, and we just divide that by 2, find the midpoint between those, and that's its average speed. Is that okay? All right, and then our third equation that we want to use here is rate of change of speed. Okay, which is a really long-winded way of saying something. Just basically how fast you're getting faster. Okay, so for those of you who really like cars, the analogy here is if I buy myself a little 200 quid kind of beat up dying car, 1 litre petrol off a whole pile of cylinders, and I stamp the accelerator, that car will go from 0 up to 60. And therefore will have an average speed of 30 miles per hour using my average speed equation here, that I have initial speed of 0, final speed of 60, divide that by 2, 30. Right? If I buy myself a Bugatti on my ridiculously inflated teacher salary, right, I hop into that and I thump the shoe on it, I go from 0 to 60 with an average speed of 30. But these experiences are not the same because my Bugatti gets to speed faster. Okay, it gets there quicker. So my rate of change of speed is how much faster do I get faster. It's a really weird kind of concept. So what we need to do is we need to figure out, well, what is my change of speed at the top? So I need to know what was my change of speed, and then I want to figure out and how long did that take me. And we're going to divide that by the time, because the longer it takes me, the lower my rate of change of speed is. So it's on the bottom line of this. Now, for those of you who've done a little bit of revision already, you're probably not used to calling it rate of change of speed. What you're probably more used to calling this is acceleration. Okay, and it's almost right. Technically speaking, and this is very technical, acceleration is change of velocity divided by time. And in almost all situations that we will run across, especially in year 11, where these two things are basically the same. Okay, they're not exactly the same, and there are big differences when you get a little bit further up the school and further into your physics studies. There are big differences between rate of change of speed and acceleration. But for now, change of speed, these are pretty interchangeable, rate of change of speed and acceleration. Okay, now change of speed can then be broken down a little bit further to be final speed. I should change that back to the black color because that's what we're doing. That would be, how would you find your change of speed? Well, what you do is you take your final speed. I, for some reason, cannot select my previous color, which is a bit annoying. Let's try that again. This is the new version of Notebook, which I'm still figuring out, but we will get there. Just change it back to black. There we go. Final speed, take away the initial speed. Notice that this is a minus sign here now, which is different to this equation up here. Again, a mistake that people make is that they slightly get that one wrong. And then we've got to divide that by the time taken to get that equation. Final speed minus initial speed. Is that all right? Okay, any questions? Just checking a look in the commentary here. Holy unicorn moment. All right, other than that, everybody seems to be fine with the actual physics content. More my daughter's LED setup in the background. Right, okay, moving on. Are we all happy with that so far? These are our key equations for this section of the content. We will want to add a few more onto these, and we will want to add some letters in here because this is a lot. Okay, this is a lot by way of words. If you're answering an exam question, it is completely legitimate to use words for your equations, though it does slow you down a little bit. Okay, so quick then recap. We're going to pop into the corner some of the equations that we'll want to have here. So speed equals distance divided by time, shortens to S equals d over t. That average speed, and they do like the average, strangely, is equal to, right, initial speed u, okay, final speed v, and then all divided by 2. Maths purists, I should have brackets on the top line there, technically I suppose, so that we don't end up falling foul of BidMass, but you know, we can be sloppy sometimes. On occasion. Right, there we go. So that's average speed is u plus v over 2. The idea of the u plus v thing, straighten that up, is very difficult. The idea of the u plus v concept is that if v stands for velocity, and again, speed and velocity are not the same thing, but they can be used sort of interchangeably sometimes, that if v is your final speed, then u is the letter before v. So it's the thing that comes first. So it's your initial speed plus your final speed divided by 2. And then your rate of change of speed, which tends not to get too much of an equation, so we will write it as acceleration because we want to use the u and v terminology, is v take away u. Okay, so notice the switch around here because we need the change of speed and we start with our final speed. Even if that final speed is lower, okay, because we can end up with a negative value here and that is fine. So we're going to do v take away u and then we're going to divide that all by t. And we're going to need to be able to rearrange these equations nicely. All right, all happy? All right, cool. So then once we're able to actually calculate these things, what we then have to be able to do is we have to be able to draw graphs and extract information from these graphs. And everybody loves a good motion time graph. All right, now, there are two types of motion time graph, and we're going to take a look at both of them here. In all cases, they will have time across the bottom. Okay, so that's good. Okay, you'll have time across here. And then up the side, you will either have some word like distance, displacement, or possibly, you know, some arbitrary unit like how far away, or something weird like that. You know, just something to just put you on your guard but it'll be something measured in meters or kilometers or some form of distance measurement up the side. So we'll get a distance up here. And then we'll get a graph that looks maybe a little bit like this. So it goes across, and then it goes flat, and then it goes up again, but slightly different, and then it goes flat again. And what we'll be asked to do is to make some calculations or make some inferences about this. Okay, so let's label this. We have an object, and this thing's moving as time goes on, and we're going to try and describe how it's moving. Now, I've got no numbers up the side, but I can put some in a little bit later on for illustration purposes. But we want to just kind of discuss what's happening here. Right, so I'm going to start here. And the reason I'm going to start here is this is where time is 0. Okay, and time is 0 when I decide to start timing. Okay, this does not mean at the moment of the Big Bang or the moment that the universe or the Earth was created or whatever it is you want to think about that. It's just whenever I decided to start timing this object. Okay, and then as time progresses, so time goes on here, I end up at this time here. And in that time, I have steadily increased my distance. Okay, really smoothly up this line. Okay, no deviation, no squiggliness, no nothing along here, and I've ended up in this position. I am now further away than I was. I've travelled some distance in a given time. And I could find my average speed by using this equation here. That my average speed is my distance travelled, which is this number, take away this number, okay, which is 0, and then divide it by the time, which would be this number. Now, the savvy amongst you who love maths, and that is all of us, let's be honest, will understand that if I do the change of distance here, which would be the y-axis value, divided by the change in the time, which is the x-axis value, I would be accidentally doing the rise divided by the run of this graph, which is the gradient. Okay, so if you're good at calculating gradients, you can just go up gradient of the graph. That's the average speed. So for this one, the average speed is the gradient of the graph. The gradient is fancy word for slopiness. Or steepness, to use words that actually exist. Which is always a good idea when you're communicating with people. Okay, so gradient is the steepness. The steeper this graph is, the higher the average speed. The less steep this graph is, the lower the average speed is. Okay, on this little section here, which is fun, it's completely flat. That I start at a certain distance, so let's get a little purple marker here. At this time here, I start here, and I don't go anywhere for a period of time. And if I start at a certain place and I don't go anywhere for a particular period of time, then that means I'm not moving. And we can write not moving, that is acceptable on an exam, but at rest is the fancy way of saying that this object is at rest. Okay, because it's not necessarily true, pardon me, my glasses are a little bit steamed up. It's not necessarily true that it's maybe not moving, it could be oscillating, it could be vibrating back and forth, it's just not going anywhere, so it's at rest. Once again though, we head off at this time and we seem to climb this little section here. And we again can calculate how fast we're going using this speed distance time equation, because I know how long it takes me to get from this point to this point. I need to be a little bit careful because it's not just whatever I say here, it's actually the difference between these two numbers. From here to here is my time, and then how far I travel is the difference between where I start and where I end up. Okay, so it would be the difference between those two numbers. I hope that makes sense. All happy? So once again, I end up with a gradient calculation, or I just put in the distance traveled divided by the time taken in my equation, and I can find my average speed. Now that average speed is going to be nice and steady, so we can say that even no matter what the number is, we can say that this is traveling at a constant speed in that section. Okay, so in here, it's traveling at a constant speed. It is traveling at a constant speed here as well. I know some people who are really kind of mathsy inclined go, it's traveling at a constant speed here as well, that constant being 0. That's not okay to say. You can't say it's traveling at a constant speed of 0, because the implication of saying it's traveling at a constant speed implies 1, it has a speed, and 0 is when you say, it's the number you use to indicate that you don't have something. You know, you don't say, I have 0 Ferraris sitting in the driveway. You just say, I don't have a Ferrari. Okay, it's slightly different to I have 1 Ferrari, 2 Ferraris, 3 Ferraris. I don't have a Ferrari is what you say when you have none. So here, you don't say you have a constant speed of 0. That is not okay. You simply say you're at rest. Okay. And then once again, up here, we are further away than we were at the very start, but we are still not changing our speed in this section here. So we are again at rest. Okay, the GCSE further miles ones are fun. Yeah, I agree. Okay, all good. All good. So that is what happens, and this is called a distance time graph or a displacement time graph. That you have displacement on the y-axis and time on the x-axis. And to be honest with you, that's the hardest bit. The hardest bit is actually realizing, what am I dealing with here? What do I actually have to solve? And so as an exam tip, the very first thing you should do when you see one of these is lock your eyes onto this y-axis and go, what am I actually doing here? And be really careful with the unit, because if I do the gradient of this graph, I will have the change in the y-axis, which will be something measured in meters, and then I will divide that by some form of time, probably in seconds, and I will end up with a unit of meters per second. And that is the unit for speed. So I'm dealing with speeds here from my gradients. Is that okay? All right, now, having said all that, let's take all of this out, if I possibly can, in one fell swoop. I'll probably take out the axes as well. Yeah, I'll leave that one. Okay, and I'm going to change this axis title. And instead of distance, displacement, and how far away, I'm going to write in speed. S-P-E-E-D. I can write also velocity, or I can write in how fast, which would be a really weird thing to write, but you know, possible. So speed, velocity, and how fast at the side. But on the bottom, I will once again have my trusty unit of time across the bottom. So these are motion time graphs. There's something going on the y-axis, and then time is on the x-axis. Make that a little bit bigger. Okay, in this case, we'll draw actually pretty much the same graph. It goes up like that, it comes across like this, and it goes up a little bit slantier than that. I'm going to add a little strange section here at the end. I'm going to come down here, and then I'm going to go across the bottom like this. Okay, because this one's a little bit more complicated. All right, so what's actually happening here? Let's take a look at this. And I would encourage you, if you're looking at these questions, to actually go, right, what's happening? And ask yourself the question before you get stuck in. Once again, I start at time 0. And I seem to be doing much the same thing. I'm traveling along, and I end up at time here. But this time, I'm not actually traveling a distance. All I've got told here is that my speed changes from 0 to not 0 up here. Okay, so if I do this number, take away this number, I wouldn't calculate the change in distance this time. What I would calculate would be the change in speed. Does that make sense? Okay. And if I then divided that by the time it took, I would get an equation that said change in speed divided by time. And going back to our original equations, change in speed divided by time is our rate of change of speed, or our acceleration, if we're being a little bit, playing it a little bit loosey-goosey with our language here. So we can say that for that one, rather than having a nice steady speed here, because we don't, our speed's changing, we're definitely not traveling at a constant speed, because I start at 0 and I get faster. My speed is very much not constant here. But what I can say is that I have a steady acceleration. Now, I'm going to do something very dangerous here, which is I'm going to tell you what never to write. And always the danger is that somebody has nipped off to make a cup of tea somewhere, and they're going to come back and they're going to go, oh, that looks interesting. So what I'm about to write here is what you never, ever, ever, ever write in an exam. And that is, you never write that you are accelerating at a constant speed. Okay, do not write that. Do not write that. Definitely don't write it in the Year 11 exam. For those of you who are here for the nostalgia, having headed off in upper sixth, you will know that in upper sixth it is possible to accelerate at a constant speed when we do circular motion and we go round, round, round. It is possible to accelerate at a constant speed, but accelerating at a constant speed basically implies that you're getting faster whilst not changing speed. It implies that, and that is a contradiction. Okay, so therefore should never ever be written. You have a steady acceleration. Okay, like I say, when I get you further up the school again, I'll show you a couple of exceptions, because like all things, we build and we build and we build. So, you know, it is what it is. In this situation here, we have, well, that's what's happening between here and here. I have a speed of something here, and that speed does not change until I get to here. And if my speed doesn't change, then I must be traveling at a constant speed. So that's a constant speed. Next little section, I start here and I end up here. And again, I have a change in speed happening, and I have a time that it took. But notice that this line is a little bit steeper. So the time it took me compared to the speed I increased is a little bit shallower than this one. I changed speed more rapidly here than I did here. Okay, the gradient of this section is larger. The gradient here is, the gradient of this section is a little bit less than the gradient of this section over here. Okay, and because this gradient is less, we can say that this is a steady acceleration, absolutely. But we can be a little bit more precise. It is but less than before. You're not accelerating as sharply here. You're not changing speed just as rapidly as you were at the start. And if you had numbers, you could do the calculation. You could go, what is the change in speed? How long did it take? Calculate the acceleration, job done. Right, so notice that we had the same shape, but we had very different things happening. Where it was at rest before is now constant speed. Where it was constant speed, it's now steady acceleration. Okay, because we've changed what's on our y-axis. This bit, we start with a high speed and we end up with a low speed. All right, and this is where this equation is important. Okay, change in speed is great, divided by time. This is better. Final velocity, take away initial velocity, divided by time is what we want. So we want our final velocity down here, which is 0. Okay. And we want our initial velocity up here, which is not 0. Let's say it's 7. So the change in speed there, if I was just doing pure change, is 7. But the final speed take away the initial speed is actually 0 take away 7, which is -7. Okay, and then however long that takes, we would divide that through. So let's say it takes 2 seconds, because that makes the maths easier, and we like that. I would then calculate that the acceleration is equal to -3.5. The unit for acceleration is meters per second squared, which we will come to in a second. All right. Basically what acceleration says is that's how fast you're getting faster. This thing is not getting faster, so therefore it has a negative number. It is decelerating. Okay, so we can call this the acceleration is -3.5, or we can say that the deceleration is equal to 3.5 meters per second. It is getting slower by 3.5 meters per second every second. The other word that we use for that is retardation. Okay, it is getting slower by 3.5 meters per second squared. And this is a spec point. You do have to be able to use this terminology, okay? So deceleration, slowing down, and retardation, same concept, the rate at which you are losing speed. Is that all right? Okay, now, hello Imran, how are you? What we now need to do is, there is one last little bit of information that we can gather from this graph. What we're going to do is, I'm really going to quickly, I hope I'm going to quickly, rub out all my inking over this so that we can draw a little bit more stuff on it. There we go, that was quick, that was nice, yeah. What if I wanted to calculate how far I travelled? Because I can just tell you how much faster I'm getting, what speed I'm doing here. But let's say I wanted to know how far did I travel between these two times. It's at a constant speed, so that's pretty handy. I would just use, well, I've got speed equals distance over time, so I can rearrange that to distance is equal to speed multiplied by time, multiplying both sides by t. Okay, the speed is whatever this value is here. Okay, so that's kind of the height of that line. So the distance is equal to, let's give this some numbers just for the sake of making the point. So let's say that this is 10 meters per second up the side here. And let's say that this time is 3 seconds here. And let's say it is 6 seconds over here. I can do what I like with those scales. Okay, so it starts off doing an average speed of 10, and because it's at a steady speed, its average speed is 10 the whole time. Multiply the time it does that for, which is 3 seconds, because the difference between 3 and 6 is 3. And therefore the distance it travels is 30 meters. Is that all right? Okay, so we can just calculate that out using that equation. I wouldn't though. And in fact, if you try to do that in the exam, they will look at you very suspiciously, because there's a little trick you can use, which is if you have a velocity time graph and you want to know how far it's traveled, you can just calculate the area between your line and the x-axis. This kind of area that I'm shading in here really badly. The area of that rectangle is the distance traveled, because it's got a height of 10 and a width of 3, making 30. Well, that's very good. But what about here, where it's not a rectangle? What if I wanted to know how far has it travelled in this section? Well, technically what I should do is I should use the equation that average speed is equal to distance divided by time. But again, you'd be looked on slightly suspiciously. But I could use the equation distance is equal to average speed multiplied by time. And I'm writing this out in full, well, for this side anyway, to make a point. That between this point and this point, the average speed is not 10. The average speed between 0 and 10 is 5. Okay, because remember, it's initial speed plus final speed divided by 2. So I have to do that equation over there using this one. So there's a little bit of a two-step problem. We don't like that. We don't like two-step problems, but we're doing them anyway. So the average speed here would be 5, and then how long does it take? Well, it starts off at 0, it ends up at 3 seconds. So we multiply that by 3, and that would give me a distance equal to 15 meters. However, what if I try to do my little area shading trick? If I try to find the area between the line and the axis here, what I have is I have a triangle. And the area of a triangle area is equal to a half of the base multiplied by the perpendicular height of that triangle. So that would be a half multiplied by the base of the triangle, which is 3 across here, multiplied by its height, which is 10, which is 15 meters again. Isn't that cool? Now, it just so happens that it's the area under here. Now, if I wanted to find the distance traveled by this whole thing, what I could do is I could break up all of this into little sections of triangles and rectangles and calculate it all out, which is what we actually would do if we were doing something more complicated, because it gets really tedious trying to get average speed, average speed, average speed, average speed. We just go, okay, cool, I'm going to break this down. I've got some numbers across the bottom, because in a proper question it would have numbers all around the place, and you'd be able to just pick them off. So I'd maybe draw a line down here, and that's going to generate a little triangle in here that I can calculate the area of. And then I'd probably go with a line across here, which would generate a triangle on top there, and then another rectangle down here. And if I was doing it sensibly, I would have just made that all one big rectangle. But it doesn't matter, you can do it as multiple rectangles, multiple triangles, whatever you want. Break it down and get the area under your graph to work that one out. Is that all right? Okay, so this is probably the most difficult concept in all of graphing in year 11 stuff. This is one of the worst done questions there is going. Most people get 0. most people, well, not most, 50% of them get 0 marks for this question. And the reason they get 0 marks is they're asked to find the distance travelled. They immediately go speed equals distance over time. They pick a single number from the graph. They do the whole time for the whole thing, and there's nothing there. The first mark you want here is you want to go, the distance travelled is the area under the graph. Write that statement out, and then just break it down nice and logically, and just add them all up. Job's a good one. Okay? Right, that's most of motion taken care of. Now, next bit. We're running at 9 o'clock here, so we'll maybe not get onto forces this time round because I don't want to keep you too long. I want to keep these to half an hour. I'll maybe do another, we'll do forces as a separate topic next week. Okay, but anyway, before we get on, we want scalars and vectors. It's a pretty quick concept to get to it. Okay, scalar quantities, if you're measuring anything in physics, okay, you generally have some form of number, 590, and you have some form of unit, meters. Okay, and 590 meters for certain things is enough. Okay, if I tell you, however, to stand in the middle of a field, boom, like that, and I tell you to walk 590 meters and walk, and just leave you alone, just go walk 590 meters, then some of you, go and do that in your head, just pick a direction, close your eyes, stand in the field, and I want you to walk 590 meters. Now, the unimaginative amongst you will walk 590 meters straight, that way. The slightly more imaginative will decide that they want to go in a completely different direction. So you end up going all across here, 590, 590, 590, 590. I do want to say the people who might need a little bit of a chat with somebody, some of them will go, you only told me to walk 590 meters. You didn't tell me to keep walking. So what I might do is I might go there, and then there, and then there, and then there. You didn't say in a straight line. I didn't say in a straight line. I just said 590 meters. And what would happen is if I got all of you, the millions upon millions of people that are currently watching this live stream, to walk 590 meters and then stop, what should happen is I get an even distribution all the way through this circle of people who walked all the way to the edge and stopped there, people who walked all the way to the edge and stopped there, and some people who just took one step back there, one step back, and just stayed exactly in the middle, and everything in between. Okay. That is because I simply told you to walk a distance of 590 meters. Okay. Now, if I said something slightly different, if I'd said, I want you to end up 590 meters away from the center of this circle, or away from the middle of the field, then suddenly your ability to kind of mess with me is heavily restricted. All you can do at this stage is walk 590 meters in a straight line, or at the very least, if you're going to walk more than 590 meters to end up 590 meters away. Again, there are some people who like finding ways around rules. I did say end up 590 meters away from the center, that you could have gone, all right, I'm going to mess with you, I'm going to walk 700 there and then come back to here. Perfectly fine. But at the end, I know you are somewhere on the edge of this circle, because I gave you a direction, sort of. I just said away. Now I could be even more precise. I could say, I want you to walk and end up 590 meters straight up the screen away from the center of this circle, or from the center of this field. At that point, the circle goes away. You have one option, which is you travel 590 meters and you end up there. And I know exactly where you are. You have no choice in the matter. Okay, this is the difference between a scalar and a vector. A scalar quantity has a size and a unit, but a vector quantity has an additional bit here. It has a direction. And it can be as vague as straight up the page, or it can be as precise as 119.45 degrees north of the equator, starting at whatever your starting point is in the middle of the equator. Geography is not my thing. Okay, does that make sense? So scalars, if you're ever asked what the difference between a scalar and a vector is, the funny thing when people ask you what a difference is they don't want the difference at all. They want you to tell you what the two things are. Scalars have magnitude. That's fancy for have a number. And unit. What did you measure? You've got 590 what? Meters, feet, inches, if you're American, that's fine. Okay, 590 Tesla, 590 amps, 590 volts, 590 meters squared, 590 yards, 590 whatever. Okay, vectors have magnitude again. They have all this stuff as well. They need a magnitude and unit. Cardinal sins of grammar. I'm going to put two ands in a sentence, but I'm going to capitalize one. And direction. And once you add a direction to something, you end up with a vector. Okay? And you have to know some of the differences and some of the names of them. Okay? So common examples, and that's where we're going to finish tonight because you've been a great audience. Scalars, vectors. Okay? So things that have just got size. Things like length, general distances, areas, time. Okay, 5 seconds. You can't go 5 seconds up. Okay, you're stuck with that. These are scalar quantities. Okay, mass, how heavy you are. Okay, how much stuff there is in you. Vectors, however, are things that have directions on them. Okay, like forces, which we haven't done tonight, but we will do. We can push, pull, and twist something. If we push something to the left, it is a completely different situation to if we push something to the right. So the direction of that force matters. If you're talking about how far away you are from somewhere in a given direction, you're not talking about distance technically, you're talking about displacement. Okay, how far did you end up traveling from that object? Speed is a vector, 60 miles an hour, 70 miles per hour, 30 meters per second. We'll put it in this list here because it's an important one. But it has an equivalent vector quantity, which is called velocity. If the object is traveling 50 miles per hour, 50 miles per hour forwards is very different to 50 miles per hour in reverse, especially if you're sitting in your driveway. Okay, that is the difference between, well, 50 miles an hour in your driveway is probably a really bad idea, full stop. But, are you going straight into your house or are you actually going out onto the road? Okay, so forces, displacement, and velocity are very good examples of vectors. And your last one then is acceleration. And that's why rate of change of speed is slightly different, because speed is a scalar and rate of change of speed is also a scalar, despite how my little table's trying to make it look as if it's not. But acceleration is not, and that's why it's not quite the same to say it's change of speed. It is change of velocity divided by time taken, but it's close enough in almost all cases because people use velocity just mean forwards anyway. Okay, so hopefully you've got something out of that. If you are prepping for an exam, your exam is in 4 weeks' time. We should be looking at past papers now, trying to hit up a couple of past papers a week. This is going to be a weekly lesson up until then, so we've got 4 weeks of year 11 cramming to do on a Tuesday evening. So hopefully you can join me again next week. If this was in any way useful, I do appreciate a like. Not that it does anything for me, this isn't monetized, but it just makes me feel happy that I get appreciated, and I will see you in the next one. Thank you so much for joining me, and don't forget everybody, physics rocks. It's true.